You have a 24GB card. The model file is 16GB. You do the obvious subtraction, decide you have 8GB of room to spare, and load it. And it works. It loads clean, it answers your first question fast, everything is fine. Then you paste in something long, a real document, a repository, a transcript, and one of three things happens. It refuses to start at that length, or it starts and your speed collapses to something unusable, or the whole thing falls over with a memory error on a card you were certain had room. Nothing is broken. Your subtraction was just incomplete, because the model file is not the only thing that has to live in your VRAM. There is a second consumer, it is invisible in every tier list and every best models for your GPU video, and here's the part that should genuinely change how you shop for hardware. At long context lengths, that second thing can be larger than the model itself. Not a rounding error, larger. So this video does three things, and by the end, you'll be able to do all of them on the back of an envelope. First, the number nobody counts, what it is, why it exists, and the one line of arithmetic that tells you exactly how big it will be on your machine for your model at your context length. This is the part I'd most like you to steal. Once you can do it, every tier list on the internet becomes readable in a different way, because you'll see the half they left out. Second, the two settings that actually move it, and one of them is a choice almost nobody makes deliberately, because it isn't a setting at all. It's a property of the model you picked, and it can change your memory bill by a factor of 4 before you touch a single flag. And third, the answer in the title, the exact combination that puts a 27 billion parameter model with a genuinely long context window on a 24GB consumer card. I'll show you the arithmetic that gets there, and I'll be straight with you about the combinations that don't work, because two of the obvious ones don't. One thing worth saying up front, because it's unusual for this kind of video, there are no benchmarks here and no vendor claims. Every number I'm about to give you is arithmetic from a formula I'll show you that you can redo on a calculator in about 15 seconds. Nothing here depends on trusting anyone's marketing, including mine. Let's build it. The number nobody counts. Start with why it exists, because the mechanism makes the arithmetic obvious afterwards. Your model's weights are static. They're the same size whether you say hello or paste a novel. 16GB of weights is 16GB on the first token, and 16GB on the 100,000th. That's the number everybody quotes, and it's the easy one. But a language model doesn't only compute, it remembers. Every time it processes a token, the attention mechanism needs to look back at every token that came before. And rather than recompute all that history for every single new word, which would be catastrophically slow, it stores a small piece of intermediate work for each past token and keeps it around. That store is called the KV cache, the keys and values from attention, and it has one property that makes it the villain of this video. It grows linearly with your context length. Double your context, double the cache. Every token you feed in leaves a permanent deposit in your VRAM until the session ends. So the mental model to carry, the weights are the machine, the cache is the workbench. You budget carefully for the machine, wheel it into the room, and then discover the workbench needs to be bigger than the machine to do the job you wanted. And that's exactly what the arithmetic says. The one line of arithmetic. Here's the formula. It looks intimidating spoken aloud, and it's trivial written down, so it's on screen and in the description. Cache size equals 2 times the number of layers, times the number of key value heads, times the head dimension, times your context length, times the bytes per number. 6 terms, all multiplication. Let's take them one at a time because each one is a lever we'll pull later. The 2 is because you store both keys and values, not adjustable. Layers, how many attention layers the model has. Read it from your model's config file. For a 27 billion parameter model, 64 is a common shape. Remember this term. It's where the biggest surprise of this video lies. Key value heads. And this is one place the industry already helped you. Older models kept a separate set for every attention head, which was ruinous. Modern models use grouped query attention, where many query heads share a much smaller number of key value heads. 8 is typical. If you're running a model from the last 2 years, this optimization is already working for you, silently. Head dimension, usually 128, from the config file. Context length, the one you choose and the one this whole video is about. Bytes per number, 2. If the cache is stored at 16-bit precision, which is the default nearly everywhere. Remember this term too. It's the first lever. Now run it. 64 layers, 8 key value heads, head dimension 128, 16-bit, at a modest 4 kilobytes of context, about 1 gigabyte. Fine. Invisible. This is why nobody notices the problem. At short context, the cache genuinely is a rounding error, and that's the regime most people test in. At 32 kilobytes, 8.6 gigabytes. At 128K, 34.4 gigabytes. Stop on that. Your weights were 16.2. The cache at the context length the model advertises is 34.4. The thing nobody counts is more than twice the size of the thing everyone quotes. Add them. To run this model at the context it claims to support, you need 50.6 gigabytes. On a 24 gigabyte card, you are not close. You are not one setting away. You are less than halfway there. And at 256K, a context length several current models advertise. The cache alone is 68 gigabytes, more than 4 times the weights. This is the arithmetic that every tier list omits. Not because anyone is being dishonest, the model file size is a real number, it's just the smaller half of the bill. And the gap between the two halves gets wider every time the industry brags about a longer window, which produces the line-eyed car from this whole video. Context length is not a setting, it is a hardware purchase. You pay for it in gigabytes in advance whether or not you use it. Lever 1. Quantize the cache. So how do we get from 50 gigabytes to something a real card can hold? 2 levers, and the first one is the one people have at least heard of. Look back at the last term in the formula, bytes per number. The cache is stored at 16-bit precision by default, but there's nothing sacred about that. The cache is numbers, and numbers can be stored more coarsely. Store it at 8-bit and you have it. Store it at 4-bit and you quarter it. Run the arithmetic again at 128K 16-bit, 34.4 gigabytes, 8-bit, 17.2, 4-bit, 8.6. That is a very large amount of memory recovered from one flag, and it's supported in every major local runtime. There are cache-type flags in the popular local engines and equivalent settings in the serving frameworks. The exact spelling differs and moves around, so I've put the current ones in the description rather than reading them out. Now the honest part, because this is a trade and I won't pretend otherwise, quantizing the cache costs you some quality. Not catastrophically. Going to 8-bit is generally considered close to free, and it's the setting I'd reach for first without much anxiety. 4-bit is more visible, and how visible depends heavily on what you're doing. Long-range recall and precise retrieval over a big document are the tasks where a coarser cache hurts most, which is a little cruel given that long context work is exactly why you wanted the big window. So the rule of thumb, 8-bit cache is close to free and you should probably just use it. 4-bit is a real trade, and you should test it on your actual task before trusting it. Not on a toy prompt, on the thing you actually do. But here's the thing about lever 1 on its own. Take the best case. Conventional model, 128K, 4-bit cache. Cache is 8.6. Weights are 16.2. Total, 24.8 gigabytes. On a 24 gigabyte card, you are 800 megabytes over before accounting for any framework overhead at all, which in practice means it does not fit. That is a genuinely frustrating result, and it's where most people stop and conclude they need a bigger card. They don't. They need the second lever. Lever 2, the term nobody thinks of as a lever. Go back to the formula and look at the second term, layers. Everyone reads that as fixed. It's a property of the model. 64 layers is 64 layers. What's there to adjust? Here's the thing. That term isn't really how many layers does the model have. It's how many layers keep a cache. And for most of this technology's history, those were the same number, because every layer used traditional attention and every layer therefore had to remember. That is no longer true. A newer family of architectures, the hybrid designs this channel took apart at layer level a couple of weeks ago, replaces traditional attention in most layers with a linear attention scheme that keeps a small, fixed-size running state instead of an ever-growing history. Those layers still do their job. They just don't accumulate a cache that grows with your context. So a model can have 64 layers where only 16 of them carry attention, in a 3-to-1 ratio. And when you put that into the formula, the layer term drops from 64 to 16, and the entire cache drops to a quarter, at every context length, before you touch any setting at all. Run it. Hybrid architecture, 128K, standard 16-bit cache, 8.6 gigabytes. That is the same cache size the conventional model needed 4-bit quantization to reach, achieved here at full precision, purely by which model you chose to download. This is the lever nobody pulls deliberately, because it doesn't look like a lever. It looks like an architecture diagram in a paper, but it shows up on your invoice in gigabytes, and for a local user, it is the single highest leverage decision on this list. And notice what it means for how you shop. 2 models, both 27 billion parameters, both roughly 16 gigabytes of weights, both claiming the same context window. On the spec sheet, they look interchangeable. In your machine, at long context, one of them needs 4 times the cache memory of the other. No tier list will tell you that. The config file will. Stacking them. The answer in the title. Now put both levers together, and here's the arithmetic that pays off the title. Hybrid architecture, 128K context, 8-bit cache, 4.3 gigabytes, weights, 16.2, total, 20.5 gigabytes. That fits on a 24 gigabyte card with roughly 3.5 gigabytes of headroom. And you want that headroom for reasons I'll come to. Push one step further. Hybrid, 128K, 4-bit cache. Cache, 2.15 gigabytes. Total, 18.3 gigabytes. Comfortable, nearly 6 gigabytes spare on a 24 gigabyte card running a 27 billion parameter model at a context length that, on a conventional architecture, would have demanded 50 gigabytes. That's the answer. A 27B model at 128K on 24 gigabytes is not only possible, it's comfortable. If and only if you pick a hybrid architecture model and quantize the cache. And I want to be equally clear about what does not work, because half-truths in this genre cost people money. Conventional architecture at 128K on 24 gigabytes does not fit. Not at 16-bit, which needs 50 gigabytes. Not at 8-bit, which needs 33. Not even at 4-bit, which lands at 24.8 and spills. If your model keeps a cache in all 64 layers, that context length is not available to you on that card, and no flag will rescue it, which is a genuinely useful thing to know before you spend an evening trying. Why this got worse, not better? One short detour, because it explains why this problem is newer than it looks, and why the advice you absorbed a year ago is now wrong. 3 things happened at once. Context windows exploded. A model advertising 4,000 tokens 2 years ago carries a cache measured in hundreds of megabytes, genuinely ignorable. The same architecture at 250,000 tokens carries a cache measured in tens of gigabytes. The formula didn't change. The context term went up by a factor of 60, and it multiplies. Weights got smaller, quantization worked spectacularly. A model that needed 60 gigabytes at full precision runs in 16 at 4-bit, which is wonderful. And it means the weights shrank while the cache grew, so the ratio flipped. There is a crossover point in every setup where the cache passes the weights, and for most people running long context today, that crossover is already behind you. You are past it, and nobody told you. And the advice didn't update. The rule of thumb everyone learned, take the file size, add a bit, that's your requirement, was accurate in the short context era and is simply wrong now. It's not that anyone lied, it's that a true heuristic aged into a false one while the vocabulary stayed the same. So if you've ever bought a card based on, this model is 16 gigabytes, so 24 is plenty, you weren't being careless. You were applying a rule that used to work. The rule just has a term missing, and the missing term is now the bigger one. Lever 3. The context you don't ask for. There's a third lever, it costs nothing, and it's the one I'd actually reach for first. Most serving setups allocate the cache for the maximum context you declare, not for what you happen to use. Ask for 128K and you reserve 128K worth of memory, even if every conversation you have is 4,000 tokens long. The memory is gone the moment the server starts. So the honest question, do you need 128K? For a lot of real work, no. Interactive coding on a handful of files, chat, drafting, most agent loops. These live comfortably inside 32 kilobytes. And the difference is not small. The same hybrid model at 32 kilobytes with a standard 16-bit cache needs just 2.15 gigabytes, for a total of 18.3. You get full precision cache, no quality trade at all, and it fits with room to spare. Whereas if you declared 128K just in case, you'd have paid 4 times that in memory for context you never filled. The cheapest context is the context you don't ask for. Set the limit to what your work actually needs, measure, and raise it when something truncates, rather than reserving the maximum on day one and wondering why your card feels smaller than the spec sheet promised. What to actually do in order? 6 steps, and none of them require trusting a benchmark. 1. Find your model's real shape. Open its config file on the model hub. You want the number of hidden layers, the number of key value heads, and the head dimension. 30 seconds of reading. 2. Check how many of those layers are attention layers. For a conventional model, it's all of them. For a hybrid model, the card or the architecture section will tell you the ratio, and that single fact is worth more to you than any benchmark score on the page. 3. Run the formula at your target context. 2. Times attention layers, times key value heads, times head dimension, times context, times bytes. Do it at 32K and at 128K so you can see the slope. 4. Add the weights and leave headroom. Take the Quantize file size as the weights figure, then leave roughly 10% of your card free on top of the total. Activations, framework overhead, and memory fragmentation all need somewhere to live, and a plan that fills your card to the last megabyte will fail in practice even when the arithmetic says it fits. This is why 20.5 on a 24 gigabyte card is a good plan and 23.8 is not. 5. Set the cache precision 8-bit as your default. 4-bit only if you need it, and only after testing on your real task. 6. Measure the thing you actually care about. Load it, feed it a genuinely long input, and watch your memory and your tokens per second. The arithmetic tells you whether it can fit, only your machine tells you whether it's pleasant. The ladder, rebuilt honestly. Here's what I'd like to replace the standard tier list with, and it's a change of format more than of content. Every tier list you've seen maps a card to a model. That mapping is incomplete because the same model is two completely different memory bills at two different context lengths. The honest unit isn't which model fits on my card. It's which model at which context fits on my card. So the ladder becomes 3 columns instead of 2. And the rough shape from the arithmetic on 8 to 12 gigabytes. You're in the territory of smaller models, and the cache is your binding constraint far earlier than people expect. This is where declaring a modest context and using an 8-bit cache turns a card that can't run anything into a card that runs plenty. On 16 gigabytes, a mid-size model at a working context is comfortable. That same model at its maximum advertised context usually is not, and a hybrid architecture is what closes that gap. On 24 gigabytes, as we've just worked through, a 27 billion at long context is achievable with the right architecture and cache setting, and out of reach without them. And above that, the arithmetic stops being the interesting constraint and bandwidth takes over. But that's a different video. The point of the reframe, stop asking what fits, start asking what fits, at what context. The second question has a real answer, and the first one never did. Honest limits. 5. 1. The arithmetic is exact. The model numbers are yours to check. The formula is correct and reproducible, but layer counts, key value head counts, and head dimensions vary per model. I used a common 27B shape as the worked example. Read your own config file rather than assuming mine matches. 2. I did not benchmark anything. No tokens per second, no quality measurements, no head-to-head. This video is arithmetic and mechanism. Whether 4-bit cache degrades your task is a question only your task can answer. 3. Real usage carries overhead I've deliberately left out. Activations, framework buffers, fragmentation, and anything else on your card, including your desktop. That's why I keep insisting on roughly 10% headroom instead of computing to the last megabyte. 4. Implementations differ. Some engines allocate the cache lazily rather than upfront. Some use page schemes that change the picture. Some quantize keys and values differently. The formula gives you the ceiling, and the ceiling is the number that decides whether a plan is possible. Your engine may do better. 5. This moves. Cache quantization support, flag names, and architectural ratios all change between releases. The arithmetic won't change. It's multiplication. But the flags will. So check current documentation rather than a video, including this one. Step back, because underneath a memory calculation, there's a shift worth naming. For 2 years, the entire local AI conversation has been about weights. How many parameters? How hard can we quantize? How small can we make the file? Every tier list, every will it run video, every hardware recommendation has been a conversation about the size of one file. And while everyone was optimizing that file, the industry quietly moved the cost somewhere else. Context windows went from 4,000 tokens to 1 million, and the memory that a long window consumes grew right along with it, sitting outside the file, unmentioned in the spec, invisible in the recommendation. Which means a lot of the local AI advice in circulation is answering a question from 2023 with confidence. In 2026, the file size era is over. We're in the context era, and the bill is different. The good news, and it is genuinely good news, is that both fixes are available to you right now, today, at zero cost. One is a flag, the other is a download decision. Together, they turn a 50 gigabyte requirement into an 18 gigabyte one, which is the difference between I need to buy a workstation and the card I already own is fine. And that gap between what people think their hardware can do and what it can actually do is almost entirely made of arithmetic nobody showed them. So here's my question, and I'll pin it below. Run the formula on the model you're using right now at the context you actually declared and post the number. Model, card, context length, and the cache size you calculated. I want to see how many people discover that their cache is bigger than their model, because I suspect it's most of us, and a public list of those numbers would be a more useful buying guide than any tier list, including the one I just described. Every link, the formula written out, the current cache precision flags for the popular local engines, and this channel's teardown of the architecture that makes the 4 times difference is in the description. That's the standard here. No benchmarks, no vendor claims, one formula shown in full, every number reproducible on a calculator, the combinations that don't work named as plainly as the ones that do. And the honest answer that a 27 billion model at long context fits on a 24 gigabyte card only if you make 2 specific choices. If you'd rather own your tools than rent them, subscribe. That's what we do every single day. I'll see you in the next one.